Hey guys, welcome back to the channel. Today's video, we're going to be taking a look at streamlines and pathlines in two-dimensional flow with a worked example. So, a streamline, when we have our fluid particles, a streamline is going to be a tangent velocity vector on a field. So usually our particles, we can describe our flow with what's called a velocity field, where we have a velocity at different spatial coordinates as well as time. So if we have our, let's say our x, y, z plane, we'll have a velocity here, velocity here, velocity here, and remember these also vary with time. And remember these are also composed of their respected components. Okay, so that's use v, and this is just equal to I and j. So I'm just referring to this velocity field is going to help us out with streamlines. So if we break this down and we take a look in a 2D plane, we're going to have our x, our y, and we have our velocity vector. The x and the y can be modeled as dy, since it's the velocity vector, dy and dx, right? And we can actually equate these two. This is just going to be y over x. So y over x, I'll write that a little bit neater. Y over x, this is going to be the y component, and this is going to be our, so this is going to be our y and our x, which is also going to be equal to our v and our u, where v represents the vertical component of our velocity and u represents our horizontal component of the velocity. So let's take a look at path lines now. So path line, we essentially get that from following a particle's, kind of like its journey over time, but we're following it very closely. So in order to describe its position, since its position changes over time, its x position, we can model it as dx over dt equals x and dy over dt equals y. So now we have these equations. Let's go ahead and start working on the problems. So velocity field is given by v equals axi minus ayj. The units of velocity are meters per second. X and y are given in meters, and a is given as 0.3 seconds per second, or like a second raised to 1, -1. So obtain an equation for the streamline in the xy plane. Let's set up the differential equation. Dy over dx is equal to negative I believe this was what? Oh, y, yeah. Negative ay x. These a's will cancel out, and if we go ahead and solve this equation, we'll get 1 over y dy equals negative 1 over x dx. So if we go ahead and solve this, we'll get natural log of y equals negative natural log of x plus c. And I want to get these in terms of y, so we're going to use this. We're raising everything to e, so we can get rid of this natural log. Y equals, so this is going to become x raised to -1, and that's just going to be 1 over x, and e raised to c, that's just going to be c And because remember our exponent rules, these are going to multiply. So if we want to solve for what c is, which is our initial condition, we can say c is equal to y initial x initial, which is just equal to y times x, or x times y, however you want to put it. So first part is done. Let's go ahead and write a here. And now let's go ahead and move on to b. So plot the streamline passing through the point x initial y initial equals 2, 8. So x initial is going to be 2, y initial is going to be 8. If we plug those in to get what c is going to be 16. And remember that these were in meters, right? So we'll get meters squared. And let's make our graph, right? So this is our graph. And x initial 2. So I'll write like 1, 2, 3, 4, so on and so forth. And 2, 3, 4, 5, 6, 7, 8, so on and so forth. A little bit messy. Sorry, my handwriting is not the best. And it's gonna be 2, 8. So let's draw a little point at 2, 8. And my graph is 1 over x. Y equals 1 over x. And I know that's like, and gonna be like an it's gonna be like logarithmic. We're gonna have like a logarithmic decrease. So it's gonna be like something like this. And now we plot the streamline, okay? So that's out the way. We're gonna write down b here. Just want to keep my work a little bit organized. B. And B is done. Let's go on to C. Determine the velocity of a particle at the point 2, 8. So our velocity field is given here. We need to plug in 2, 8 and see what we get. So we know that A is equal to 0.3. So I'm going to write down my given here. A equals 0.3. And our velocity function is given by 0.3. Remember, it was a times x. It's going to be 2 minus and 0.3 times 8. We can quickly go up here and verify that my equation is correct. And now if we just plug this into the calculator, we'll get 0.6 for a horizontal component and negative 2.4 for our vertical component. Let's go ahead and, so at that point 2, 8, we're gonna have, let's think about it going down like 0.6, or sorry, going down by negative 2.4. And going to the right is 0.6, and our velocity vector is going to look something like that. So this is going to be C. And now we got C out the way, we can move on to D. So if the particle passing through the point x, y is marked at time t equals 0, determine the location. So if we want to determine the location, we can actually use the path line. Because remember, we're following this particle closely, whereas here in the streamline, we're looking at the velocity. So if the particle at t time t equals 0, determine the location of the particle at time t equals 6. So time equals 0, we're going to be over here. So let's go over and see. So our equation is going to be dx over dt equals ax, and dy by dt is equal to negative ax. Now all we have to do is just separate these just like we did before, and so now I'm going to take a out of the integral because it's constant. We'll have dt, and I'm going to integrate this from 0 to t because we're starting at t equals 0. And here I'm going to have 1 over x dx, and we're going to integrate that from our initial x to our final x because we know already what our initial x is. And we're going to set that equal. And here we have our dy over dt. So if we go ahead and do the same thing here, oh, this should be a y. I don't know why I made that an x. Equals 1 over y dy from y initial to y final. And now let's just integrate. So it's going to be the natural log of x minus x initial, and I'm simply just going to use my log rules here. I'm going to skip a step, but I can show that to the side really quickly. This should be an absolute value. Equals, this is going to be a times t. I'll write the steps out real quick. And here, this is going to be same as this, where we have our natural log of y over y initial. You can just refer to those steps is equal to, and you can refer to those steps again. And now we're going to raise it to e, and simply just going to get x over x initial equals e raised to at, y over y initial equals e raised to negative at, and if we solve for x and y, x equals x initial e raised to the at, y equals y initial times e raised to negative at, and the problem asks, determine the location of the particle at time t equals 6. So I know what x initial is from earlier. If you guys want to go look at my graph, x initial equals 2, y initial equals 8. We're going to have 2 here. I have 8 here. E 0.36, 8 e negative 0.3. Wait, yeah, 6. 6 is correct. Okay, and we'll just solve for our position at time t equals 6. So for x, I got x equals 12.1. Oh my gosh, this again. Y equals y equals 1.32, and these are both at t equals 6. So this problem D, yeah. So So we're gonna know like at time t equals 6, at t equals 6, our particle is gonna be like, our particle is gonna be way out here, somewhere here. We're gonna be where our particle is gonna be, and now we finished with d. Let's take a look at this. What is the velocity of this particle at time t equals 6? So all we have to do really is just plug everything in. So let's recall our equation. And we'll just plug everything in. So 0.3, 12.1 minus 0.3, 1.32. I'm gonna get 3.63i minus 0.396j, or I should have rounded that up, but it's okay. This is gonna be problem E. Let's see what that would look like. So it would look something like this, right? We're gonna have our vertical component of like 4-ish, and our horizontal component of 4-ish, sorry. And our vertical component is gonna be like this. So it'll be something like that. And now we got one last problem left. Show that the equation of the particle path line is the same as the equation of the streamline. So the case where our path line and our streamline would be the same is if we have what's called steady flow. So let's quickly see, do we have steady flow? And steady flow means that our properties don't change with time. So if we have a property, say like n, we had like dn over dt, it would just be equal to 0 because it's not changing over time. So now we can see what our two equations were. So our first equation was like xy. This was our equation for our streamline. So I'm going to denote that as stream, because that was equal to c. And our path, I believe it was x over, yeah, equals e raised to at, and y over y initial equals e raised to negative at. So first things first is we need to get this in the form of xy into one equation as x as a function of y, or y as a function of x, however you want to say it. So e equals at, I can plug that into, I know what that's equal to here, so we can put that here. But let's solve what e equals at is here. So this is also equal to 1 over e raised to the at, y over y initial, and we just flip these, we take the reciprocal, and we have, oh, I did not mean to switch to red, equals e raised to the at. So now we know y initial over y equals x over x initial, and we need to see, are these two equations equivalent? If we cross everything, we get x, y equals x initial, y initial, and these are actually the same equation. So we have steady flow. And that was the last problem. So let's take a look at all of this. Oh. Okay. So yeah, it was a nice problem, and I hope you guys learned some concepts from that problem about, Streamline. Okay, for some reason it keeps zooming in. Microsoft Whiteboard hates me. So I hope you guys understand now streamlines and pathlines. Thank you for watching.